Good morning or good afternoon for good morning for A1 and good afternoon for A3. So I'm going to be out for a couple of days, and these videos are going to help you do the notes in class. They're going to help you do the homework and your exit tickets as well. So today we're going to build off what we know about perpendicular and angle bisectors. So before we do that, I need to give you a couple of definitions. So when three or more lines intersect at one point, the lines are said to be concurrent. And the point where they intersect is called the point of concurrency. So if I take a look at, like if I just draw three lines right here, this point right here, we call this the point of concurrency because it's where three lines meet. Okay? So that leads us to our first theorem called the concurrency of perpendicular bisectors. And this states that the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. So what do I mean by that? Let me choose another color for this highlight. So what do I mean by that? So let's take a look at this diagram right here. So here we have three perpendicular bisectors. And we know they're perpendicular bisectors because they're perpendicular to the sides and they split the sides into two equal halves. So here we have a line that's perpendicular and splits the side into two equal halves. Here we have a line that's perpendicular and splits the line into two equal halves. So right here, these are perpendicular bisectors. Point P, which is right here, P is the point of concurrency because it's where three lines meet. And what this is saying is that the perpendicular bisectors, they're concurrent at a point that is equidistant from the vertices. So here are the vertices of the triangles A, C, and B. And what this is saying is that PB is equal to PA is equal to PC, meaning that the point of concurrency is equidistant from all the vertices of the triangle. Okay? All right. So let's explore this more with the scenario to the right. I want you to write down what you notice and wonder. So please pause the video, write down what you notice and wonder, and then we'll talk. Okay, so hopefully you paused the video and wrote down what you noticed and wonder. So what I noticed is that there is a triangle inside a circle. And so what I wondered was, how is this related to perpendicular bisectors? Question mark. So let's explore this further right here, okay? So we have this circle. Here's the center of the circle. So this is the center of the circle. And the distance between the center and the outside has a special name, which you guys know is the radius. So here, that's the radius. And what do we know about the radius? Well, we know the radius of a circle is always constant, meaning it never changes. So because of that, because the radius is always the same, we can say that the center of the circle is equidistant from the vertices of the triangle. So here are the vertices of the triangle. So here we have vertices of triangle. So the radius of the circle is always constant. Therefore, the center is equidistant from the vertices So therefore, this is the point of concurrency for the perpendicular bisectors. Okay, so this circle has a special name. This is called a circumcircle or a circumscribed circle. So the circumscribed circle, it relates to the perpendicular bisectors. It's the circle that touches the vertices of the triangle once, and it sits on the outside. The center of the circumscribed circle is the point of concurrency for the angle bisectors. So this is the point of concurrency for the perpendicular bisectors, excuse me. So this is the point of concurrency for the perpendicular bisectors. And I want you to note that the circle is on the outside while the triangle is on the inside. So we're going to see a case where that's different. Okay, so now we've talked about perpendicular bisectors. Now let's look at angle bisectors. So we know angle bisectors, they split angles into two equal halves. So split angles into two equal halves. So this theorem is saying that the angle bisectors of the angles of a triangle are concurrent at a point equidistant from the sides of the triangle. So what do I mean by that? So here we have the angle bisectors. We know that these are angle bisectors. So green is angle bisectors. And we know that these are angle bisectors because they split the angles into two equal halves. And this theorem is saying they are concurrent at a point. So here our point of concurrency is Q. So Q is the point of concurrency at a point that is equidistant from the sides of a triangle. So Q is equidistant from the sides of the triangle. Or in other words, QM is equal to QN is equal to QO. So for perpendicular bisectors, the point of concurrency is equidistant from the vertices, whereas for angle bisectors, the point of concurrency is equidistant from the sides. So the point of concurrency for perpendicular bisectors is called a circumcenter. So for perpendicular bisectors, we call it a circumcenter. For angle bisectors, we call the point of concurrency an incenter. All right, so let's look at this example right here. So I'm going to work with this one through you, and then I'm going to ask you to do the next one on your own. So here we have a bunch of angle bisectors. Let's see here. So here we have the angle bisector for angle K and the angle bisector for angle L. So let me draw this out. So here we have this angle bisector. Here we have this angle bisector. And we know that they are going to meet at the incenter. So this is the incenter because it's the point of concurrency for the angle bisectors. So therefore, this incenter is equidistant from all the sides of the triangle. So because of that, we can say QP is equal to RP. So 3x plus 1 is equal to 5x minus 3. So then we just distribute this and this. So that's 3x plus 3 is equal to 5x minus 3. So that's going to be... So let's see, let's subtract 5x from this side, subtract 5x. So that's going to be negative 2x plus 3 is equal to negative 3. So negative 2x is equal to negative 6. X is equal to 3. And the problem is asking us to find RP, so then I just substitute that into the expression. 5 times 3 minus 3 is 12. Okay? So now I want you to try this problem on your own. Please pause the video, and then we'll work through it together. Okay, so let's use the figure shown. So here we have a angle bisector, and here we have an angle bisector. So I know automatically that this is the incenter. So this is the incenter. So that means that the incenter is equidistant from all the sides of a triangle. So let's look at part A. So in part A, they tell us BAF is 15 degrees. And so because this is an angle bisector, we know this is 15 degrees as well. And the measure of angle A is just 15 plus 15, or 30. It also tells us that CBF, so here CBF, is 52 degrees. So that means this part is 52 degrees. And the measure of angle B is equal to 104 degrees. And it's asking for what is the measure of angle ACF. So they want this thing right here. Well, I know that angle C is going to be bisected. And I also know that the measure of angle A plus the measure of angle B plus the measure of angle C has to equal 180 degrees because they're all inside of a triangle. And I know that this is 30 degrees, this is 104 degrees, and we can just call this x right here because we don't know it. And if we solve, we get x is equal to 46 degrees. So the measure of angle C is 46 degrees, but we want ACF, which is the bisected angle. So to find that, I would just divide that number by 2, and I would get 23 degrees. So the measure of ACF is 23 degrees. Okay, so now if we look at the next part, it tells us EF is equal to 3y minus 5, and DF is equal to 2y plus 4. If you haven't already, please pause the video and work this problem out yourself. So pause right now. Okay, so it's asking for what is the distance from F to AB. So here is F. What is the distance between F to AB? And we know that the incenter is equidistant from all sides of a triangle. So therefore, EF has to equal DF. Or 3y minus 5 is equal to 2y plus 4. Therefore, y minus 5 is equal to 4, or y is equal to 9. So DF is 2y plus 4, so that's 2 times 9 plus 4, which is equal to 22. Okay? So that's equal to 22. So this is 22, this is 22, and because they're all the same, this is 22 as well. So our answer is just 22. All right? Okay, let's move on. Here's, if you want to pause and see the work, you can do that right now. Okay, so let's review some definitions. In a right triangle, there is one angle with the measure of 90 degrees. So this should all be reviewed because we've discussed this. In an acute triangle, all three angles are less than 90 degrees. In an obtuse triangle, one angle is larger than 90 degrees. So let's try to draw the circumcenter for an acute, right, and obtuse triangle. So I'm going to do the first one, and I want you to do the other two on your own. And then, so I'm going to do the first one, pause the video, and then do it on your own, and then come back to the video to check your answers. So let's draw an obtuse triangle. Let's do this right here. And let's find the circumcenter. So the circumcenter is for perpendicular bisectors. So this is for perpendicular bisectors. So let me get my ruler out. Let's see. I'm going to draw my first perpendicular bisector. So you see how that's 90 degrees. It's going to split the other side in half. So you start at the vertex, and then you split the side into two equal halves. So there's my first perpendicular bisector. So we drew a perpendicular bisector to this side right here. You can tell that those two lines are perpendicular and the original line was split in halves. It doesn't need to start, perpendicular bisectors don't necessarily need to start at the vertices. So now let's do the same for the other side. So here I have this side right here, and I'm going to draw a line perpendicular to that side, and it's going to split the side into two equal halves. And then I'm going to go here and then draw the perpendicular bisector. So you can see it's perpendicular and it splits the side into two equal halves. So you can see that the circumcenter in this case, so here's the circumcenter. This circumcenter is on the outside for an obtuse triangle. All right, so I want to make sure that you pause the video and try to see if you can draw the circumcenter for a right and an acute triangle. Okay, so now let's look at this. So I'm going to draw a right triangle, so 90 degrees. Let's put this away. So here we have our right triangle and forms a 90-degree angle. So let's try to draw the circumcenter for this right triangle. So here's the first perpendicular bisector. These two lines are perpendicular, and this side is split into two equal halves. Then I'm going to do the next one, which is going to be right here. I'm going to split this side into two equal halves and make sure that they're perpendicular. Notice they're perpendicular and this side was split into two equal halves. And then finally, I'm going to do the last side right here. So draw my bisector and then split the hypotenuse into two equal halves. So notice that here's the circumcenter, and this is neither inside or outside. It's on the side of the triangle. So for obtuse triangles, the circumcenter is on the outside, and for right triangles, it's on the side of the triangle. I bet you can guess what acute is based off of that. So if I draw myself an acute triangle right here, and let's draw our bisectors. So we have the first one, come on, 90 degrees. Split this into two equal halves. Do the same thing right here. Split this into two equal halves and make sure it's perpendicular. Go right here. Split this into two equal halves and make sure it's perpendicular. So here's our circumcenter. And this is on the inside of the triangle. And so those are our three cases for the circumcenter. Now I want you to take a second and see if you can determine whether the incenter can ever be located outside the triangle. So the incenter is for angle bisectors. I want you to determine if the incenter can ever be located outside the triangle. So please pause the video and try this problem. And you might want to refer to this theorem right here. Okay, so if we think about what it means to be an incenter has to be equidistant from all sides. So if we have like an incenter right here, the incenter has to be equidistant from all sides of the triangle, because that's what an incenter It is equidistant from all sides of the triangle. It's for angle bisectors. So if we go back here, if we try to put an incenter on the outside, there is no way it can ever be equidistant from all sides of the triangle. So if I put it right here, that is definitely closer to one side. If I put it right here, that is definitely closer to these sides than it is there. If I put it right here, it is closer to this side than the other two sides. So the answer is no, because the incenter must be equidistant from all sides of the triangle. Okay, so now let's fill out this summary table. Okay, so we have our circumcenter. So this is where all the perpendicular bisectors meet. And the circumcenter is equidistant. Let's zoom in right here. It is equidistant from the vertices. And the circumcenter can be located outside the triangle. So I want you to do this for the incenter. I want you to fill out the table for the incenter and see what you can get. So please pause the video, fill out the table for the incenter, and then come back for the answer. Okay, so we have our incenter. This is where all the angle bisectors meet, and it is equidistant from all the sides of the triangle. And as we just discussed, the incenter can never be located on the outside. All right, so the last part I want to talk about are circumscribed and inscribed circles. So circumscribed circles are for circumcenters. So if I have this circumcenter, which is equidistant from all the vertices, the circle will be on the outside. So the circle is on the outside, and the triangle is on the inside. So the triangle is on the inside. So we have this circle right here with the center at the circumcenter, and the circumcenter is equidistant from all the vertices. For inscribed circles, which is for incenters, we have the triangle on the outside and the circle on the inside. So here we have the incenter, and the incenter is equidistant from all the vertices, from all the sides, The incenter is equidistant from all the sides of the triangle. And then we have our circle on the inside. Notice that the radius of the inside circle is just the distance between the incenter and the side, whereas the radius for the circumscribed circle is the distance between the circumcenter and the vertex of the triangle. So the radius is the distance between the circumcenter and the vertex, whereas here the radius is the distance between the radius is the distance between the incenter and the side of the triangle. All right, so that is it for today. Please complete this exit ticket. They are no longer for participation, so I need you to do this with accuracy, and please turn it in to the substitute. Thank you and have a great day.